Okay. So today we are going to discuss continuous Markov processes. Right on the edge. So these are the three lessons, lesson 9, 10 and 11. These are the background of module 2 or frequency division approach. Okay. In the next class you will see exactly what frequency division approach means. So draw this process. This is a typical Markov process. Okay. Draw this, I will explain. Draw this diagram. Okay. So there are two states, state 1 and state 2. Okay. And whatever numbers you see here, these are the probabilities. Okay. If a system is in state 1 at the current instant, what is the probability that it will remain in the same condition in the next time instant? For example, now it is 11 am. The temperature is supposed to say 27 degrees centigrade. So what is the probability that it will remain at 27 degrees centigrade at 11 am? Now it is say 12 pm. So what is the probability that it will remain at same temperature at 1 pm? So that probability is half, 50%. What is the probability that the temperature will be 30 degrees at 1 pm? That probability is also half. Also, suppose the system is at 30 degrees centigrade at 1 pm. What is the probability that it will continue to be in the same state at 2 pm? Probability is 3 by 4. What is the probability that it will revert back again to 27 degrees centigrade at 2 pm? 1 by 4, 25%. So these are known as transition probabilities. These are known as transition probabilities from state 1 to state 2. Okay, and this is known as a discrete Markov chain. The above system shows a discrete Markov chain where the probabilities of remaining in or leaving a state in finite time are shown. Okay, and all these probabilities can be represented as a stochastic transition probability matrix. Stochastic originally represents probabilistic. Stochastic originally represents probabilistic. The other part of stochastic is answerable, which cannot be given any probabilistic number. Okay. So whenever you are in a two-state system, you have got 4 transition probabilities. The probability that the system will remain in state 1, provided it is in 1. The probability that the system will move to state 2, provided it is in 1. The probability that the system will move to state 1 from 2, state 2 from 2. It remains at state 2. What are the probabilities? So from here you can see P11 is half, P12 is half, P21 is 2 to 1 is 1 by 4, P22 is 3 by 4. So this is the transition probability. That means suppose these are two temperature state, two in-speed state, okay, or two load states in the power system at 11 am and 12 pm. So if you know the data at 11 am, you can simply multiply with the transition probability to get the state at 12 pm. But what will be the state at 1 pm? Again, you will multiply with again the transition probability, that is p square. Okay. So just like here, where just write down where Pij is the probability of transition to state j after a time interval given that it was state I at the beginning of the time interval. Okay, write down what is Pij. Probability of transition to state J after a time interval given that it was in the state I at the beginning of the time interval. So after the second time interval, that means I told 11 am, 12 pm, 1 pm. After the second time interval, we can simply make P square. P square as in matrix multiplication. Okay, P dot P is as in matrix multiplication. So P square means this one. Okay. Square. P square is this square. Okay, I forgot the square term here. Okay, clear? What is a discrete Markov process? You have different states, so that's a discrete Markov process. Which state probability is known as transition probabilities. Now, what are continuous Markov process? So this was a discrete Markov process. So what are continuous Markov process? Reliability problems are generally associated with systems that are discrete in space. That is, they can exist. They can exist in one of a number of discrete and identifiable states and continuously in time. Okay. Thus, they can exist continuously in one of the system states until a transition occurs which takes them discretely to another states. Okay, so they can exist in any number of discrete states and they have certain probability to go to another state. So next you write down this one. What is a stationary Markov process? Where the transition probability does not change with time. Okay. So from 12 pm to 1 pm, 1 pm to 2 pm, 2 pm to 3 pm, 3 pm to 4 pm, the probabilities of change are always the same. Okay. That is known as a stationary Markov process. Okay. So a stationary Markov process are those where the conditional probability of failure or repair during a fixed interval of time is constant. Okay, write down this. What is a stationary Markov process? The definition. Now, if you consider a single repairable component which has with the failure and repair rate, so consider, note this. What is failure rate? How is it represented? What is the term symbol for the failure rate? Last class we have seen it is lambda. Lambda is the failure rate. What is the repair rate? Mu. Okay. Lambda is the failure rate. Mu is the repair rate. Both are constant. That is, they are characterized by exponential distribution. Okay. So this is something you remember. There is some derivation behind it from reliability engineering studies. We are not bothered about that. We just say that failure rate and repair rates are characterized by exponential distribution. Okay. So this is a single repairable component that we have seen in the last class. Okay. So in this case, you have state 0, the component is operable. State 1, the component has failed. Okay. Transition from operating state to failed state is characterized by the failure rate lambda. From the failed state to the operating state is characterized by the repair rate mu. Okay. We define P0t, which is the probability that the component is operable at time t. P1t, the component is failed at time t. So in that case, lambda is the failure rate, which is given by 1 by mttf. This we have already seen in the last class. And mu is the repair rate, which is 1 by mttr. The transition, now you have to write the transition rate. Just write down the last one. The transition rate is defined as number of times a transition occurs from a state divided by the time spent in the state. Okay? Number of times a transition occurs from a state divided by time spent in the state. Now what exactly are lambda and mu? So lambda and mu are basically limiting state probability. We need not write, we just go through the slide. The failure rate and repair rate can be understood as lambda means number of failures of a given component in a given duration divided by total period of time the component was operational. Because it is the failure rate. Here total period of time when the component was operating, what is the number of repair of a component in that given duration? Okay, that is the repair rate. This is the limiting state. The limiting probability is given by P0 probability for infinite duration given by n by n plus r or mu by lambda plus m. This we have seen in the last class. Okay. Now this is a single component system where we have a partial output case. So draw this diagram. Okay. Draw this diagram. So in this case, the difference with respect to the two-state system is that we have a three-state system. So 0 means full output. 1 means partial output. 2 means the system has failed. Okay. So as you see here, what is lambda 1 mean 1? Lambda 1 means when the generator is giving its full output, say 100 megawatt, what is the failure rate that it gives only 50 megawatt? Okay. Partial output. Okay. Suppose the rating of the generator is 200 megawatt and it is giving 100 megawatt. Then it is partial output. The probability of failure is lambda 1 in that case. Now suppose we correct the failure and repair the generator, then what is the probability that it will again go back to 200 megawatt generation? So that is known as the repair rate, mu1. Okay, lambda 1 and whereas suppose I'll say 100 megawatt and here I will say 200 megawatt. This is full output, this is partial output. Now suppose it is operating partial outputs and something further fails. So in that case, with the failure rate of lambda 2, it goes to failed state. That means the output is 0. Okay. Now when the output is 0 megawatt, what is the probability that again we can make the generator generate at least 100 megawatt? Mu. That is the repair rate. Okay. For state 2. Okay. Similarly here you see, when it is failed, what is probability that it will directly go to the full output state? Mu. Okay. And if it is in the full output state, what is the probability that it will completely be out of service? So that is lambda 3. That is how we need to be understood. So this is a three-state system. Clear? This is a three-state system. Now you have got two repairable components. You need not draw it. You just understand. Okay. We have got two components which are repairable, which can be repaired. Generators. So you have got generator up, generator 2 up. Here in state 2, this is state 1. In state 2. Generator 1 down, but generator 2 is up. In state 3, generator 1 is up, but 2 is down. And in state 4, both are down. So accordingly, you can understand this repair rates and failure rates. Okay? This is just another extension of what you have seen there.
So DN is down.
Which one?
Down.
Down. DN means off, out of service. Okay. Next, state diagram of two identical components. So suppose these are all from the Millington book. So for two identical components, you can have both components up, one component up, that means partial, or both fail. Okay. Now since these are identical components, failure rate is lambda. Okay. And repair rate is mu. Okay. When both components are up, okay, and you need to go to only one failure, okay, then it is lambda. Okay. From here to here also it is lambda, combined it is 2 lambda. Okay, that's what it says. Okay. This is only for reference. Now this is the one that we will be using for our frequency and duration approach. So this model you have to draw. Okay, this complete model. So how you will start? So there are 3 generators here. Okay, you take a complete portrait page, a new page. You don't do it in, because you will be needing space. And this is the diagram that we will be using in our next class for computation. So do it clearly. Okay. So I will explain this diagram. So So here there are three components, three generators. So here there are three generators. U means up, okay. G means down or out of service. Okay. In the first state, if you see, in the first state, all the generators are up. All the generators are up in service. Okay. So that is state 1. In state number 2, to get from state 1 to state 2, you have a failure rate of lambda 1. That means the generator 1 has failed. Okay. Okay. Lambda 1 is generator 1 has failed. But other two are in service. Suppose 2 to 3. 2 to 3 there is no connection because here we are only considering single state transition. Single state transition. That means only one generator will change it from up to down. If you see from 2 to 3, D U U U D U. Okay. That means the second generator is down. From this state to this state, from 2 to 3 state, second generator has become up to down and first generator has become down to up. So we are not considering that type of transition. We are considering only one transition. Okay. For example, from state 2 to state 5, if you see, lambda 2 is there. That means generator 2 has become out of service. Okay, so there is only one transition. Generation 1 and 3 remain the same. Okay, so in this case, since we are considering two outputs, okay, either up or down, we are considering two outputs, and there are three generators. Total number of states is equal to 8. Okay, so there are two outputs and three generators. Okay, two outputs and three generators. So total number of states is 8. So maximum number of states in this case is 8. Okay, so all the 8 states you can draw. Okay, but once you have drawn first step is draw all the 8 states, considering the different condition of the generators, combination of the generators up and down. But transition can occur only where there is a single transition, up to down, down to up for only one generator. If there are more than one transition, we do not make that arrow transition. Okay, we are only considering the single state transition that will be used for frequency and duration approach. Okay, so draw it completely. Okay. Now, the topic of the next class will be frequency and duration approach. Okay. So where we will take the same system. Okay. Three generators which can transition between all these 8 states, and we will find out the transition probabilities as well as the state frequencies. What is the frequency of each state and what is the probability of transition between one state to the other state. Okay. So this can be that this plot can be understood to be for the above system. So any generator is either up or down. Okay. Now when it is down, R is the time to repair, isn't it? And N is the time for which the generator is operating. Okay? And T is the total duration. Okay? So from this, what can be the other kind of indices which can be used for such a system? First is frequency of encountering a system state. So all the 8 states that you have shown there, what is the frequency that a generator will be in, or a system will be in a particular state? What is the frequency that all the generators will be up? What is the frequency that one generator is down, generator 2 is down, and 1 and 3 are up? Okay, that is frequency of encountering system states, and average duration for residing in that state. Okay, the evaluation is based on state space diagrams. The diagram that you have just drawn is known as a state space diagram. So mention there state space diagram for the 3 generator system. State space diagram for the 3 generator system. Okay. So we have M. M, as I said, is the mean operating time or mean time to failure. So you mentioned there in this diagram you draw and mention there. M is the mean time to failure or MTTF. R is the mean time to repair or MTTR. And T is the whole cycle time between operation and repair, which is equal to mean time between failures. So this is known as mean time between failures, which is 1 by frequency. Okay. So mean time between failures is the mean time between failures, and F is the cycle frequency. Okay. So with this we conclude this lesson. In the next lesson, we will take the same system, 3 generator system, and I'll show you in the Excel sheet how the frequency and the transition states or transition rates are computed. Okay. For all our calculation purposes, lambda will be the failure rate and mu will be the repair rate. Okay. So stop here.